Okay, so just writing out what this expression means, simply you start with the idea, what happens if u changes by a little bit? Well, a small change in u causes x to change, right? Which in turn changes f. Okay, well, that gives you this. Small change in u changes x at this rate, and f changes at this rate with respect to x. Okay? Put that together, get a picture of it. Also changes y, causing an independent change in f. So this change, here's your change, the rate at which you change with respect to y. Multiply that by the rate at which f changes with respect to y. You get the rate at which f changes with respect to u because of changes in y. Okay? And this is independent. Okay, these changes are independent. Why? Because you go to this parallelepiped, this slope is independent of this slope, and it's this slope that causes this change, and this slope that causes this change. And the smaller your delta x's and delta y's get, and they will get small, okay, as long as x and y are differentiable functions of u, okay, the closer this is to truncated parallelepiped, truncated rectangular parallelepiped, okay? In other words, the closer this surface here is to a tangent plane, and the closer the change at this diagonal is to the sum of this one and this one. Waving my hands, but you know what the picture is, okay? Okay, so what's this going to be? You want to tell me?
Partial f with respect to x times partial x with respect to v.
Yeah. Now, it's a direct imitation, but the reasoning is this, and if I change u to v, I get the same, you know, all the words are the same except for the change. Now we're talking about v, right?
Because v does the exact same thing as u.
Well, v isn't the same as u
Well, yeah.
because v drives these things in a different way than u does. Okay, actually pretty much the same here, but different here, right? Okay? Now, what if x was a function of u, v, w, and q?
Then
You would still have additive changes, so you just keep adding expressions, right? Okay, there's nothing mysterious about that. Once you understand what happens with two variables, okay? We'll write it out because there's a subtlety. I mean, it's this expression that then becomes, well, we'll talk about it in a minute. Okay, there's something we need to talk about. It's a little, well, we'll make sure we get it, but the expression is easy to understand, okay? And the relation to these is easy to understand. And then you can kind of think about why they are what they are. And I might not actually even talk about that today. Just get these ideas down, okay? Because the rest of them pretty much follow. Okay, well, you know, that's kind of pretty much the main ideas of the chain rules, okay? And if it was an f of x, y, z, and when you had an x, a y, and a z function, we just add a partial with respect to z.
What if u and v were functions of t?
Well, then you would have a dt here and here and here and here. Okay?
So t would change u, which would change.
Yeah, well, you'd have, you know, du dt here and a du dt here, right? And a dv dt here and a dv dt here. Okay, so, and I was thinking about doing that, and then I went off to something else. So, you know, okay, if okay? Change in t drives a change in u. There's a rate at which t drives a change in u, right? And then x is driven by the change in u at this rate, and f is driven by the change in x at this rate, and those rates are multiplicative. And then, of course, you do the same thing and of course, you could have just factored the whole thing out, just all this times du dt, right? And okay, well, okay. df dt is this. This is the change due to changes in u, right? T drives u. T also drives v. So we have okay. And the expression I didn't write down over here and really should have is that here never mind. Yeah, here it's okay. Okay? Now we could also write a differential. Okay? So from this we could say that df equals, and I'm going to use a more briefer notation, okay? So essentially, we've got our UV plane, okay? So we have some value of u and v, right?
Hey, where are you going? The car is that way.
And u changes by a little bit. And v changes by a little bit. So now, maybe we got, I don't want to put too much notation in this, but this point is u naught v naught, so this point is u naught plus delta u v naught plus delta v. Okay? So what's the change in f due to these two changes? Well, the change in f due to the change in u is this, and the change in f due to the change in v is this, right? Without going through a bunch of diagrams, okay? And we could do a parallel pipette in the UV plane and see where the change in u is, where the change in x is due to the change in u, and the change in y is due to the change in u, okay? And then take those changes, slap them down on an xy plane, and see where that goes, okay? And I don't want to go to that level of complexity, partly because of time, partly because I want you to kind of think it through, and I've given you enough to think through, so I'm just giving you a hint here as to where to go to understand this differential, okay? But basically, and You have to put a U and a DV on here, okay? And this gives you the approximate change in F due to changes in U and changes in V. Just analogous to a differential of a function of one variable, which of course you need to really think about and understand before you have a complete understanding of this. Okay? Now, again, on one level, these are formulas you can use. They're not that hard to remember because there are patterns to them. And you see those patterns if you sit down and try to memorize these formulas without understanding them. Best to go ahead and memorize the formulas without understanding them while you still think about understanding them, or think about understanding them and use that as a help to remember them, right? Gives you two ways to understand the formulas and apply them. And gives you much more powerful understanding, okay? So that's kind of what I recommend.